Howdy, my name is David Parker, and this is my project presentation for ENTC641. My data analysis is on earthquakes from 1990 to 2023. So up until a couple years ago, there hasn't really been extensive research done on earthquakes. Recently, we've started to expand our monitoring capabilities and research on these earthquakes, and we still don't have a consensus on how to predict their behavior, such as where they're going to happen, what depth, how long they're going to last, how strong, like a magnitude they're going to be. And so this data analysis is hoping to understand some of the trends so you can start working to be able to predict these future earthquakes, because up until now we can't. So the independent variables that are going to be used in this data analysis is going to be the time period, like what day and what year the earthquake happened, how deep, and which region they're going to be in. We're going to be focusing on two regions. We'll be focusing on the Ring of Fire, and the other regions will be everywhere excluding the Ring of Fire. And then our dependent variable in this data analysis is going to be the magnitude. And so this data analysis hopes to see if there's any statistically significant patterns that can be found between these sets of variables. So for the methodology of this data analysis, we are going to start with using a Python mapping script to visualize the data. The data that's going to be visually represented is going to be the depth and magnitude of all the earthquakes from 1990 to 2023, and it's going to be split up into the Ring of Fire region and the non-Ring of Fire region. And then we're going to hop into Excel and plot some basic trend lines to see the change in behavior. And then by behavior, I mean depth and magnitude of earthquakes in each region. And for the t-test, we're going to see if there's a statistically significant change in magnitude over time. So we're going to be comparing historical data to more current data on magnitude. And then we're going to finally do a ANOVA test to see if there is a significant difference between the magnitude of earthquakes at different depths. The final two tests, the t-test and ANOVA test, will also be done in Excel, and each of those will have 3 tests done, one for the whole world, one for the Ring of Fire, and a final one for earthquakes not located in the Ring of Fire. So here's the results. We'll start off with a map of non-Ring of Fire earthquake magnitudes. As you can see, majority of them are in the light pink to purple, meaning they're all under a magnitude of 6. This next map is non-Ring of Fire earthquake depths, and as you can see, they're all dark blue, excluding a couple of outliers, so that means they're all under 100 kilometers in depth. This next map is showing the magnitude of Ring of Fire earthquakes, and as you can see, majority of them are in the light pink, excluding Alaska, which is kind of an outlier since they have more frequent earthquakes at a lower magnitude. And so this means the rest of the Ring of Fire is experiencing earthquakes well above 5 in magnitude on the Richter scale. This final map is showing the depth of Ring of Fire earthquakes. And as you can see, there's a lot more orange and yellow in here. And so that shows that the Ring of Fire is more common in this region to have deeper and deeper earthquakes. So here are some trend lines looking at all the earthquakes recorded in this data set. And as you can see, the magnitude of earthquakes over the years has gone down while the depth has increased. These trend lines are now focused on earthquakes not in the Ring of Fire, and you can see that the magnitude has decreased significantly more in the non-Ring of Fire than compared to the world, and what we'll see on the next slide in the Ring of Fire, but the depth of the earthquakes has not really changed. As for the Ring of Fire, the average magnitude of the earthquakes has decreased, but you'll see on the right hand side the depth of the earthquakes has gotten significantly deeper compared to the non-ring of fire, and then we can account this to more activity along the fault lines in this region. So here are the t-tests done. The table on the left is for all earthquakes in the data set. The table in the middle is for earthquakes not in the ring of fire, and the table on the right is for earthquakes within the ring of fire. At the top you'll see the dates we chose to split historical to more current. And then all the t-tests show that there is a statistically significant difference between the historical mean magnitude and the more recent mean magnitude. This is our first ANOVA test going over all earthquakes in the dataset. The 4 bins for the following ANOVA test are extra shallow depth, any earthquake less than 4 kilometers deep, shallow, which were earthquakes between 4 and 8 kilometers deep. The medium depth bin is any earthquake 8 to 19 kilometers deep, and the deep bin is any earthquake who's deeper than 19 kilometers. As you can see, the average magnitude of the earthquakes does increase with the depth, and that there is a significant statistical difference between each of the bins. This ANOVA test is for earthquakes outside the ring of fire. The bin constraints are the same, and we still see that as the depth increases, magnitude increases, and that there's a statistical significance between each of the bins. This is our final ANOVA test. This is looking at earthquakes within the ring of fire, and this ANOVA test follows the same outcomes as the previous 2. So in conclusion, earthquakes from 1990 to 2023 have been on average declining in magnitude while increasing in depth. The t-tests have also shown that there is a significant statistical difference in the magnitude of more recent earthquakes compared to their historical counterparts, and this is true across all regions. And for the ANOVA test, it shows that there is a positive relationship in between the depth of an earthquake and its magnitude. The ANOVA test also shows that there is a significant statistical difference between the average magnitudes at different depths, and this is also true across all regions. Something to note is that the trend lines shown earlier do partially contradict the outcomes of both tests, but this can be attributed to more frequent earthquakes at a lower magnitude in the non-ring of fire earthquake region. Thank you for listening to my data analysis on earthquakes from 1990 to 2023. Gigamags.